Hi, I'm Jason. Let me do a quick introduction. I'm Jason Fine, Chief Architect at Absolver. Got about a decade of experience with high-scale streaming data. And really, that's kind of what my talk's going to be about, because we're going to dive into a little bit of the work that we've done. With that, before that, just a fun photo. When the days are like that, you can find me at Lake Louise. If you want to join me after, that's where I'll be. Okay, cool. So as I was starting to say, if we can get this thing, I want to talk about streaming data today. And specifically at Absolver, like Ori was saying, we get to really high volumes. So there's some challenges that build up when you're doing that. Specifically, we're going to be talking about some pull requests that I've been working on. So it's a little bit more technical, but we'll still keep it relatively high level. From the side of the query engine that improves the performance. So we have one for Presto and one for Trino. We'll dive a little bit into the technical details there. And then also from the side of Iceberg, I still need to catch up with Ryan, but we're going to talk about that with committing streaming updates to Iceberg. So beforehand, let's talk a little bit about why streaming at scale is challenging. So essentially, I'm sure all of you are familiar with some of these challenges, but the same challenges that are common across the data lake just become a lot more exacerbated when you're talking about streaming data. Like if you have changes streaming every minute, and then you have high volumes on top of that, it just becomes a lot worse. So if we look at this, first of all, we're talking about like the frequency of inserts. So with streaming, you don't really have a choice. Like you end up committing data every minute or so if you want something near real time. And that's going to lead you into like, you can't do the simple like once a day large update, which is really easy to maintain. It's going to lead you into the smaller problems. So now you end up with like the common problem of small files. And small files are going to be problematic because they have a lot of overhead. It's going to impact your query performance. And pretty much everybody knows that now you have to do like some sort of compaction in the background. Otherwise, you're not going to get good query performance. So the last thing that really becomes challenging and is kind of being worked on and improved these days a lot with Iceberg is updates. So updates used to be very difficult in the data lake. And now there's solutions that are evolving. So you used to have only one option. You used to be able to do copy on write, which means if I have some change in the data, I'm going to need to replace the entire file. And replacing it is pretty easy for the reader. Like it's got a new file, you can just consume that. But the data producer is going to have to write an entire new file, so it's very compute intensive. So it's streaming that's not going to work. The new option is merge on read, which means that you're going to produce, like Ori was saying earlier, some log of the changes, and then they need to be applied during the query. So specifically in this talk, we're really going to be talking about merge on read. Merge on read is really a necessity when dealing with streaming data. So let's see how that fits into Iceberg a little bit. So with Iceberg, they kind of standardize the way that you do merge on read. Prior to that, I think Ori mentioned this earlier, you could do like an approach like we did, which was you have a view and then an underlying table and you can merge them. But now there's like a canonical way to do it, right? So that involves positional deletes or equality deletes, and either one of those can achieve this result. We'll talk a little bit about what those are. At Absolver, we use equality deletes because producing positional deletes requires scanning the data. The reason that it requires that is like you need to tell the engine these positions in this file are deleted. So that still requires a table scan. So if you're doing high volume streaming, you can't really do that for each minute of data. So we're working with equality deletes, and that's kind of where the issues begin, and also where the solutions that I'm going to talk about begin. So equality deletes, just to be on the same page, it's a file that has equality delete fields. And if the data matches for those fields matches, the row is considered deleted. So let's have a quick look at now how you would query a table in Iceberg. So if you look at it like really high level, you have like all of the Iceberg metadata, and you're going to use the Iceberg library to build a table scan. The plan that's going to return which files need to be scanned for the current snapshot, everything like that. And then you're going to use some sort of engine to run that plan. So it's like super simple, right? Plan a thing, do a thing. But we mustn't forget that we still need to apply these merge on read changes. So we still have to apply the positional deletes, and we still need to apply the equality deletes. And these things are not like standardized. Like the spec defines that you have these things and you need to apply them, but it doesn't tell you how. So each engine is going to do it on its own way, and then you're really implementation dependent. So if we have a look at a little bit deeper into the implementation details of equality deletes, just so we understand what needs to be done later. Essentially, each operation in Iceberg has like a data sequence number. That's like the time of the operation. So everything that happens at data sequence 1 happened before data sequence 2, and so on. So with equality deletes, each equality delete file needs to be applied to all data sequence numbers that came before it. So that's the way that you can like update something. You can delete it and insert an update in the same data sequence number. It's going to delete everything prior to that and update it. OK, so we'll move on. Let's now look at like one of the implementations that's happening today in Presto and Trino. They're quite similar because they were forked from the same base, and they kind of, I think they used, maybe even cherry-picked, I'm not sure, the same commits to implement it for Iceberg. So if we have, for example, this query plan that involves, like, let's say a very simple one that has 4 data files and 2 delete files, and let's say in this case, all of the deletes apply to all the data files, the way it works is that it's going to be distributed into these splits, or divided up into these splits. And splits are like the unit of work that Trino and Presto use. And each split needs to be read, and that's going to emit your data. So in this case, it's going to take those delete files and it's going to add it to each split. And then within each split, the query engine is going to read those, and it's going to emit the data after applying the deletes. So it happens at the split level, right? So it's not happening globally or something like that. So the issue that comes up with that is that you have these 2 delete files, but now they've been read 4 or 8 different times, like twice for each data file. So it's going to add a lot of overhead. And it becomes a lot worse if you, like, for example, if you just add 1 more delete file, for example, now you're going to have that delete file distributed across all the splits, and you get 4 more file opens for 1 more file. And if we think about that a little bit deeper for streaming use cases, most of the time, most delete files are going to apply to most of your data files. That means that every delete file is going to be applied in, or going to be read in every split. Take that one step further. Let's say you have 1,000 files like this, or 1,000 delete files. That's a reasonable amount in a single day's partition. That's going to be, that's going to be about at least 1 million I/O operations. And it becomes worse because like splits, like a single data file can be many splits and stuff like that. Yeah, so that doesn't really work at the performance that you would want. So what do we do about that? So the first thing we tackled is fixing this in Presto. And in Presto specifically, you're allowed to optimize the query plan dynamically. So at runtime, we would detect if there's equality deletes, and then we would change the query plan. So if you think about it, equality deletes are essentially a join. So that's the method that we took. You apply them as an anti-join. So you take the equality deletes, you join on the equality delete fields, you filter by the data sequence number so you don't apply deletes that are too old. And then if there's no match, you can emit a row. So if we look at it, and just before I continue, This is like really useful for Presto. That's going to be doing like some native stuff. So like rewriting the query plan is also going to help down the line. So it's an approach that's pretty generic. So if we look at what that kind of looks like at a very simplified query plan, of course, beforehand, you used to have this table scan, and the data and deletes were applied, like I mentioned, within the splits. And then it would essentially emit the already deleted data. Now, if we rewrite that, we've got a table scan for the data, and we've got a table scan for the deletes. Those are scanning the data without applying the deletes at all, so they just scan the files once. We emit those. Usually it's going to be a broadcast, because usually deletes are pretty small. We join them, and we do the filtering and emit the data that's relevant. So what are the results of something like this? So we took this and we applied it on a partition that I had with about 5 gigabytes of data files and 150 delete files, and we got down from 5.35 hours to 39 seconds of compute time. This was really exciting. I was happy about that. Yeah, so we saw this works really well. So we wanted to apply it further. So we went to Torino next. And within Torino, they don't support the same plan rewriting that Presto does. So what we did is we essentially tackled the problem at the root level, at the splits reading the data. So within those, we decided to just make sure that the files are not loaded more than once. So the way we did that, and this is still work in progress, is with making the page source provider stateful. This is the component that's responsible for reading those splits and producing the data readers. We make that stateful, and that's going to allow us to share the delete files across the splits and make sure that we load them only once. So that kind of tackles the problem from there. You still have an issue where like you have some sort of read amplification because there are still multiple instances in a cluster and stuff like that, but it's negligible compared to like that 1 million IO operations. Yeah, so that's what I was saying. Okay, that's cool. We tackled the problem from the query engine side. Still, some of it's still work in progress, but it's available today, at least in Presto. I'm not sure about the releases, but it's merged. Now we wanted to talk about Iceberg, the data producer side of things. So from the query engine, once you've produced the data, there were some issues. We've addressed those, at least partially. From the data committer, you still have to produce a lot of data constantly, and if you're committing that, we ran into some performance issues as well. So what are we trying to do essentially with streaming updates? We might have multiple minutes of data being produced concurrently, and then eventually we want to commit those and apply them in order to the table. So we must apply these data, these changes in order, otherwise deletes will be applied to the wrong data or won't be applied at all. So if we take a simple example, we have key 1, it's updated at time 2 and 3, for example. That's going to be a delete and an insert. The wrong way to apply this would be you have these 2 data changes, your committer process, usually it's a separate process to reduce contention, could apply these things in a single commit. And then you have a single data sequence number, let's say 2. This is going to, as we mentioned before, the delete file is going to delete it from the previous data, so data sequence number 1, but it's not deleting it within data sequence number 2. So you end up with duplicate data. So what you really want to do is you want to produce 3 data sequence numbers or 2 extra data sequence numbers. And then the data sequence number 3 is going to delete it from the insert in data 2, and you'll end up with one data copy. So keeping this in mind, how do you produce these updates to Iceberg? So really the data files, these are produced by your query engine or your ETL tool, whatever that might be. And then you're going to defer to the Iceberg library, and it's going to produce more files for you. It's going to produce a manifest file, that points to the data file, and then it's going to produce a manifest list that points to those, and it's going to produce a metadata file that points to those, and that's going to be committed. This is essentially your commit. It's going to update the current metadata to the new metadata. So the current way to achieve what we discussed in the previous slide would be to perform multiple update operations. So you can perform multiple update operations, but the issue with that, even if you do it in a single transaction, is it's going to produce a lot of manifest files, and one for each operation. So a lot of manifest files is a little bit wasteful just from performance, and also these are kind of small files that you probably want to clean up afterwards. So it's kind of wasteful from that respect as well. So if we look at what we are trying to do, so the suggestion that we have at the moment for this is to add a new API. This is a streaming updates API, and it's going to allow you to write to multiple data sequence numbers in a single commit. So you would produce one manifest file with many changes. So if we have a quick look at an example, let's say we have 10 sequential updates that we want to apply. Previously, with the previous technique, you would end up with 20 new manifests. That would be 10 for the deletes, 10 for the update for the data files, and that takes about 24 seconds at least on my testing. With the new approach, you only have to produce two manifests, so one for the data, one for the deletes, and they contain within them multiple data sequence numbers. And that takes only 4 seconds. And as far as the upsolver was concerned, this was a huge win. So another one of those. Yeah. So really, this is kind of where our work so far has ended. But really, I think the point of a lot of this is that equality deletes, streaming updates is something that's kind of a chicken and egg problem. Like, it doesn't work too well today because people aren't doing it, but people aren't doing it because it doesn't work that well. So hopefully this work pushes us a little bit in the right direction, and people start using it more, and it becomes more mature, and then we can see where this takes us. I think there's a lot of interest in this, especially today. And yeah, that's my talk. Let's have some questions. Thank you. So time travel isn't impacted at all from, like, you can still do the normal time travel operations. If you want to time travel to older data, you would still need to keep those copies. So you might have, so you can't like have retention and time travel at the same time. So you need to choose how much storage you're willing to spend. But as far as the like external operations are concerned, like the compaction processes that would happen later and all of those, they remain identical. So like they still see multiple data sequence numbers, which is what they would have seen after like manifests would have been merged by the Iceberg library anyway. So a lot of that remains the same. Any more? Okay.
Awesome.
Cool.
Thank you so much, Jason.